While NASA's space websites go down and the sun blinds Earth's telescopes, a third confirmed interstellar object, 3I Atlas, speeds past Mars at 30 million kilometers per hour. It's the ultimate in cosmic irony. Just as this strange, emerald glowing traveler gets closer, America's science feeds go dark. Only Mars-orbiting spacecraft from Europe, China, and the UAE can seize the opportunity and reveal what the Earth cannot see, capturing the sharpest images and data before 3I Atlas disappears forever. However, as the world's best instruments pivot under pressure, what will Mars's side eyes reveal about this object that defies all comet rules? The clock on this alien encounter is already ticking. On October 3rd, 2025, the solar system's geometry will keep Earth out of the action. The sun stands directly between us and the comet as 3I Atlas passes by Mars at zero point 0.2 astronomical units, or about 30 million kilometers. From Earth's perspective, the elongation angle, the slice of sky that separates the sun from 3I Atlas, is less than 10 degrees. For ground-based telescopes, this is a hard stop. Most observatories refuse to risk their optics or sensors when a target is less than 15 degrees from the sun. By early October, the comet's position is well within the danger zone, not just for a night or two, but nearly 6 weeks, from late September to early November. Mars, on the other hand, is more than 40 degrees off-center in its orbit. On October 3rd, the angle between the Sun, 3I, Atlas, and Mars is typically greater than 50 degrees. That means Mars orbiters and surface assets have a clear view, whereas every eye on Earth is blinded by solar glare. The numbers tell the story. Earth's view is blocked during closest approach, but Mars has a front-row seat. Any change, outburst, or anomaly in 3I/Atlas's behavior during this time period will be detected first, or only, by machines circling or crawling on the red planet. Mars serves as the only watchtower in the solar system for a brief period of time. Every hour lost now represents a permanent gap in the record. The window for Mars-side observation is not measured in weeks or even days. It's only a few orbits, a sliver of time until the comet speeds away and the geometry changes again. Mission planners, who typically work on detailed months-ahead schedules, must improvise. Standard protocols are established for emergency retargeting. Instruments designed to scan Martian valleys or sample the thin air are unexpectedly directed into deep space. Data pipelines designed for slow, routine science are forced to handle bursts of raw telemetry and quick-look images in order to detect any outburst or anomaly before it fades. The pressure is relentless. Each pass overhead, each downlink opportunity, could be your last chance to capture a new feature or a sudden flare. There is no time for bureaucracy or second-guessing. Everything is dependent on the speed and flexibility of the teams operating those distant machines. Mars is orbited by a number of spacecraft, each designed for a different portion of the electromagnetic spectrum and reporting to its own mission team. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter have reserved high-cadence observation slots for the week of October 3rd. Mars Express uses a high-resolution stereo camera and an omega spectrometer to collect multispectral images and analyze chemical signatures ranging from visible to infrared. The NOMAD and ACS spectrometers on the Trace Gas Orbiter analyze the comet's light at thousands of wavelengths in search of rare gases and molecular bands. Both can pivot away from Mars to track the comet, but each maneuver is limited by thermal and safety constraints. Quick-look data may appear within days, but full public releases typically take months after calibration and validation. The HOPE orbiter from the United Arab Emirates offers a different perspective. Its XI camera and EMUS ultraviolet spectrometer, which are typically used for atmospheric science, can be repurposed to observe bright objects in the Martian sky. HOPE's global orbit and flexible pointing make it ideal for wide-field imaging and ultraviolet spectra, particularly if the science team approves a rapid response campaign. In previous comet and solar storm events, HOPE delivered processed data within a week when the results justified it. If retargeted, China's Tianwen-1, which has high and medium resolution images as well as a mineralogical spectrometer, could provide context images and near-infrared spectra, though official confirmation of a 3I/Atlas campaign is still pending. Tianwen-1 data typically enters the public domain through curated releases or scientific papers, which can take weeks or months after collection. NASA's Mars Reconnaissance Orbiter, equipped with the high-rise camera and CRISM spectrometer, has previously conducted comet and asteroid campaigns. Off-native targeting is based on pre-approved plans and spacecraft safety. Even if MRO collects new data, the current U.S. government shutdown makes public access to it more difficult. Internal teams continue to monitor the spacecraft's health and planetary protection. Beyond Mars, the European Space Agency's JUICE spacecraft will try to observe 3I/Atlas during its outbound cruise in early November. The geometry is less favorable, and its instruments, JANUS, MAGIS, and UVS, are designed for distant, faint targets. Any data gathered by JUICE will face a long downlink queue, with no public release expected until early 2026. Even a few spectra or images could help track the comet's movements as it circles the sun. This network takes a layered approach, with each mission providing a distinct field of view and spectral range. Some results will be available within a few days, while others will require months of validation. The staggered release schedule and cross-agency coordination ensure that the story of 3I/Atlas unfolds gradually. Each dataset represents a potential clue. 9 minutes. That is the duration of the Perseverance rover's unbroken gaze at the Martian sky on October 2nd. Each frame captured by the appropriate Mastcam Z includes a precise UTC timestamp as well as embedded metadata such as exposure time, filter, and camera orientation. The sequence was intended for sky surveys, but this time, a streak appears. It cuts across the star trails, not aligned with known satellites or following the slow drift of planets. The first step is calibration. Raw images are processed through a pipeline that flat fields, dark subtracts, and corrects for bad pixels. Every artifact, cosmic ray, and ghost reflection must be tracked down and eliminated. The Mastcam Z team is familiar with its calibration workflow. Compare the sky background, verify the radiance units, and align the frames. Only then does the streak become noticeable. A faint, fast-moving line that remains consistent across exposures. Astrometry takes over. Analysts use NASA's Geometric Toolkit, SPICE kernels, to translate the rover's position into sky coordinates. The predicted path of 3I/Atlas, derived from JPL Horizon's ephemerides, is superimposed over the image stack. The streak's angle and speed are measured at nearly 400 arcseconds per second, which corresponds to the comet's projected motion, as seen from Jezero crater at that time. The direction is correct. The rate is correct. However, coincidence is not confirmation. False positives should be eliminated. Cosmic rays usually leave sharp, single-pixel scars rather than long, continuous tracks that span multiple frames. Internal reflections and ghosting occur with camera movement, but this streak remains consistent. The image processors use median filters and sigma clipping to remove transients. Each candidate is measured for flux and examined for any signs of flaring or fading that could indicate a camera glitch or Martian dust. Photometry comes next. The streak is faint but consistent. Its brightness, measured along its length, is consistent with what a diffuse, fast-moving coma would produce at Mars's distance. The light curve is flat. No spikes. There are no sudden drops. Analysts contrast this with models of comet outbursts and solar reflections. Nothing is out of place. The final test is the fit. The streak's position is plotted against the predicted ephemeris for 3 comps I/Atlas. The residuals, or differences between expected and observed values, are within a few arcseconds, which is well within the margin of error at this distance. The evidence accumulates, but official confirmation remains out of reach. The U.S. government shutdown has silenced JPL's instrument leads, putting their review on hold. Independent analysts such as Simeon Schmaus and Shem Aus publish their findings, but the chain of verification awaits NASA's approval. The stakes are high. If this streak is true, it marks the first direct detection of an interstellar object from the surface of another planet. But science requires rigor. Each step, calibration, astrometry, photometry, and false positive screening must pass scrutiny. The community waits for the Mastcam Z team from Arizona State and JPL to weigh in. The streak is visible, burned into 9 minutes of Martian sky. The next step will determine whether it becomes a landmark detection or a cautionary tale. On September 25th, a single amateur observatory in Namibia provided what would be the final clear portrait of 3I/Atlas before Earth's window closed. The image, taken under southern skies just hours before the comet entered solar conjunction, captured an emerald coma that stretched nearly 700,000 kilometers across, nearly twice the distance between Earth and the Moon. The core glowed green, distinguishing it from most solar system comets. Sunlight was filtered through a cloud of diatomic carbon and other gases, resulting in a bright, almost unnatural color. However, the structure itself was even stranger. Instead of the long, trailing dust tail seen on textbook comets, 3I Atlas showed a sunward antitail, a wedge of material pointing towards the sun rather than away. This feature, shaped by large, slow-moving grains and the unique geometry of its interstellar path, gave the comet the appearance of a drifting fan rather than a classic streak. Fainter shells and arcs rippled outward from the nucleus, indicating layers or episodes of ejection rather than a continuous wind-blown stream. Follow-up image stacks from September 27th and October 2nd confirmed the pattern, albeit at a higher noise level and with glare. Even as the object faded, the coma's boundaries retained their shape, preventing the smearing and elongation typical of a dust-driven tail. Each new frame reinforced the impression that this was not your typical comet, but rather something operating under different rules, a visitor with its own internal logic. These snapshots, taken in the final days before Earth's forced blindness, now serve as the foundation for everything Mars sees next. The numbers behind 3I/Atlas do not follow any familiar pattern. Begin with velocity. Most long-period comets enter the solar system at 20 or 30 kilometers per second. This object does not slow down. It roars past Mars at nearly 60 kilometers per second, and models predict that by the end of October, it will have accelerated to 68 kilometers per second. Even the fastest comets in the solar system can't match this speed. The trajectory is equally strange. Instead of plunging in at a steep random angle, 3I/Atlases hug the ecliptic, their inclination only a few degrees off the plane of the planets. That is statistically unusual for an interstellar visitor. Most are expected to arrive from high orbits, rather than slipping in almost unnoticed along the solar system's own highway. Size is the next puzzle. Early brightness estimates combined with COMA models indicate a nucleus at least 5 kilometers across, possibly larger. That places it among the largest interstellar bodies ever discovered, rivaling the size of two I/Borisovs and dwarfing Oumuamua. But the coma itself is even more perplexing. Instead of the typical dust tail extending away from the sun, there is a sprawling layered envelope. Polarization studies point to concentric shells or arcs, each reflecting light in slightly different ways. There is no long filamentous tail, but rather a massive structured cloud that defies standard comet physics. Polarimetry and imaging both highlight the anomaly. The coma's green color caused by diatomic carbon stands out, as does its stability. Despite solar heating and a brush with a coronal mass ejection, its morphology hardly changes. The numbers, speed, inclination, size, and coma structure add up to a profile that does not fit the cometary mold. For dynamical modelers, each data point represents a new challenge, and the standard playbook provides few solutions. On September 25th, 3I/Atlas were subjected to a different type of test, a coronal mass ejection launched directly from the sun. Space weather forecasters monitored the CME as it moved through interplanetary space, predicting a surge of charged particles and magnetic turbulence. For most comets, this type of solar blast spells disaster. In just a few hours, the sudden arrival of energetic plasma can strip ions from the coma, cause rapid outgassing, and sculpt new tails. Scientists at plasma labs and solar observatories waited for a textbook response. A shock front, a burst of ionized gas, and possibly a visible kink in the comet's envelope. But reality was muted. As the CME enveloped 3I/Atlas, ground-based telescopes and Mars-side instruments monitored the aftermath. Instead of a dramatic flare-up or reshaped coma, the comet's structure barely changed. The green halo remained crisp, the anti-tail retained its wedge shape, and the outer shells showed no signs of sudden expansion or fragmentation. Morphological changes were minimal. There was no obvious ion tail, no abrupt brightening, and no ripple in the coma's layered arcs. For plasma physicists, this was a puzzle. The expectation was for more ionization, a swollen envelope, or even a hint of magnetic turbulence in the comet's light. The absence of a strong reaction raises questions about the object's composition and internal structure. Is the coma unusually resilient, or does its chemistry resist solar weather? Without a clear ion tail or a burst of emission lines, the standard diagnostic tools fall short. Researchers are now looking for clues from Mars orbiter plasma instruments and high-cadence spectra, hoping that the fingerprints of that solar storm are hidden in the raw telemetry and waiting to be discovered. The orbit of 3I/Atlas leaves no doubt as to its origin. Its path cuts through the solar system on a hyperbolic trajectory, unbound and never to return, providing a mathematical fingerprint of interstellar travel. That fact alone puts it in exclusive company with only two previous visitors, 1/Oumuamua and 2/Borisov. But the certainty of its origin is only the beginning. The real challenge is deciding what to call it and how much to trust the labels. Some researchers gravitate towards the familiar interstellar comet, citing the green coma, outgassing, and layered envelope. Others are hesitant, pointing out the missing dust tail, the anti-tail, the stubbornly stable structure, and the high, almost mechanical velocity. The debate is not only about terminology, it is also about evidence and the standard for extraordinary claims. Skepticism drives science forward as it asks not just what fits, but what survives the next round of data. The lessons of 1I/Oumuamua are still fresh. Models multiplied, speculation accelerated, but only hard numbers remained. Every anomaly, odd color, shell, and unblinking coma in 3I/Atlas must be tested rather than hyped. The question is not whether it could be engineered, but whether any measurement requires that leap. Until then, the only certainty is the interstellar passport. Everything else is a hypothesis, waiting for the next spectrum, image, or surprise. For anyone following the 3I/Atlas story, the most important tools are public data streams and community-driven analysis. Begin with the mission data portals, ESA's Planetary Science Archive, the Emirates Mars Ultraviolet Data Center, and the UAE HOPE Mission's Open Access website. Here are the first places to look for quick-look images, spectra, and event alerts. The initial results from the ExoMars Trace Gas Orbiter and Mars Express will be available within days or weeks, typically as Level 1 or Level 2 FITS files, with browse-quality JPEGs included. Independent analyst forums, such as the Minor Planet Mailing List and the Comet Observation Database, track raw uploads and flag potential anomalies as soon as they appear, providing the most timely updates. Verification occurs in layers. When a new streak or outburst is reported, cross-check it against ephemeris predictions from JPL Horizons or IMCCE. Look for similar detections in overlapping datasets, Mars orbiters, ground-based amateur networks, and even solar observatories. Community analysts frequently publish side-by-side stacks, photometry plots, and motion fits within hours, particularly when official channels are hampered by a shutdown or data embargo. To follow the morphology as 3I/Atlas approaches perihelion, track the evolution of the coma's structure with each new release. Look for sudden changes, shells, arcs, or anti-tail brightening, which could indicate new activity. The most revealing science will come from comparing raw, time-stamped images from various missions and wavelengths, rather than waiting for polished press releases. Transparency and redundancy are most important right now. Multiple instruments, independent teams, and the open release of raw data are the keys to catching what might otherwise go undetected. On October 3, 2025, 3I/Atlas passed within 30 million kilometers of Mars, while Earth-based observatories remained blind due to solar conjunction and a U.S. government shutdown. Mars orbiters from the ESA, the UAE, China, and NASA became the only witnesses, collecting data unavailable on Earth. Early images confirmed a green coma over 700,000 kilometers wide with a speed of around 60 kilometers per second, but key questions remain. The true composition of 3I/Atlas, the reason for its layered coma, and the lack of a typical dust tail. Despite a close encounter with a solar CME, the anticipated ionization effects were minimal. As international teams process their findings and prepare for staggered data releases, much remains to be explained. Although the confirmed interstellar origin of 3I/Atlas is undeniable, its nature calls into question current comet models. Until new data arrives, the story of this visitor remains incomplete, reminding us that even with global assets, some cosmic mysteries persist.